differentiate between typical and non-typical transition elements, and we learned some general features of transition elements. Students, the objectives of today's lecture will enable you to understand the electronic structure of transition elements. We are going to study the binding energies and the reason for the variable oxidation states of transition elements and their catalytic activities. We are going to learn the magnetic behavior of transition elements and the alloy formation. Students, in order to understand the electronic structure of transition elements, we are going to take the example of first D series elements to understand the electronic distribution in the transition elements. The first element of first D series is scandium, having atomic number 21, and the valence shell electronic configuration is 4s2 3d1. So these are the two electrons of 4s orbital, and the only one electron of 3d orbital is present over here. As we move on to titanium, the electronic configuration is 4s2 3d2. So the second electron is going to accommodate the second degenerate d orbital. As we move on to vanadium, the electronic configuration is 4s2 3d3. So the third electron is added in the third degenerate d orbital. Now students, for chromium, the electronic configuration should be 4s2 3d4. But over here, you can see it is a little different. It is 4s1 3d5. Now what is the reason for this change? The reason is that the d orbitals are having two more stable electronic configurations. The first one is that it should be partially filled, having one electron in each of the degenerate d orbitals. And the second more stable electronic configuration is that it should be completely filled. So chromium attains such a configuration in order to gain stability. So one of the electron jumps from 4s orbital into the 3d orbital in order to gain a more stable electronic configuration. Now the electronic configuration of manganese is 4s2 3d5. So no jumping of electron is required because it is already in a more stable electronic distribution form. As we move on to iron, the electronic configuration is 4s2 3d6. Now students, the addition of one extra electron is going to pair up one of the electron in the degenerate d orbital, and the number of unpaired electrons is going to decrease. As you have seen, when we started from scandium, the number of unpaired electrons were increasing. But from iron onwards, the number of unpaired electrons is going to get decreased. As you can see in cobalt, atomic number 27, it is going to have two paired up degenerate d orbitals. For nickel, we are going to have three degenerate orbitals which are paired up. Now students, look at the configuration of copper and nickel. The electronic configuration of nickel is 4s2 3d8, and that of copper should be 4s2 3d9, but it is 4s1 3d10. It is for the same reason that we have discussed earlier, that completely filled d orbitals is a more stable electronic configuration. So in order to gain stability, one of the electrons from 4s orbital jumps into the 3d orbital because it is going to paired up, and in this way all the 5 degenerate d orbitals will get paired up and give a more stable electronic configuration. Now the electronic configuration of zinc is 4s2 3d10, a rather more stable electronic configuration in which the 4s orbital is paired up and it is completely filled, and also the 3d10 is also a paired up and a more stable electronic configuration. So students, here we can conclude the irregularities in electronic configuration is because the exactly half filled and completely filled d orbitals, they possess extra stability. And this is the reason which explains the configuration of chromium to be 3d5 4s1 and not 3d4 4s2. And for copper, it is 3d10 4s1 and not 4s2 3d9. Now students, let us discuss the binding energies of transition elements. In order to understand the mechanical properties of transition elements, it is important to understand the binding energies. Since the transition elements are called metals, that is why over here by their binding energies we mean to say the strength of the metallic bonds that are present in the transition elements. The transition elements, they are hard, they are tough, they are having high density, they are malleable and ductile, means they can be hammered into sheets and be converted into wires. Their melting and boiling temperatures are higher than those of S-block metals. Now this is also representing that the metallic bonds in transition elements are stronger as compared to S-block metals. That is why they are having higher melting and boiling temperatures. All these properties are a measure of strength of the metallic bonds. Because along with the electrons of d orbitals, the s orbital electrons, they are also involved in the delocalization. So the metallic bonds are stronger in the transition metals. Now students, let us discuss the variation in the binding energies of transition elements. By looking at the electronic structure, we can better understand the binding energies. Now students, always remember that greater the number of unpaired electrons, greater is the possibility of that element to make bonds. So greater the number of bonds that can be formed by a single element, greater is going to be the binding energies. Now students, we are going to start from potassium, which is going to have atomic number 19 and the electronic configuration is 4s1, but there are no electrons in the 3d orbital. So you can see in this graph we are going to plot the binding energies on y-axis and the atomic numbers are going to be plotted on the x-axis. Potassium can make only one bond with this 4s1 electron. Therefore, it is going to have the minimum binding energy. Whereas for calcium, atomic number 20, the electronic configuration is 4s2 3d0. So two of these electrons can participate in the bond formation. That is why calcium can make two bonds. Therefore, the binding energy of calcium is greater than that of potassium. Students, from scandium onwards, the electron starts to fill in the 3d orbitals and the configuration of scandium is 4s2 3d1 and three of these electrons can participate in the bond formation. As you have previously noticed that scandium in most of its compound is present in the +3 oxidation states. Therefore, the binding energy of scandium is greater than that of calcium. And after that, titanium, which can use 4 of its electrons in the bond formation, is going to have a greater binding energy as compared to scandium. Similarly, vanadium. But students, look at the binding energy of chromium, which is decreasing. Why it is decreasing? Because of the unusual electronic configuration. Due to the stability of 3d5 electronic configuration, it is not going to disturb its 3d electrons and only the 4s electrons, they are going to participate in the bond formation. That is why the binding energy of chromium is going to decrease. Similarly, for manganese, you can see the binding energy is further going to drop because manganese is again in a more stable electronic configuration. That is why its binding energy is going to be less as compared to chromium. Now students, moving on to iron, which is going to be having a paired up electrons in one of its d orbitals. As the number of unpaired electron starts to decrease from iron onwards, that is why the binding energy also decreases. As you can see for iron, cobalt and nickel. As the number of unpaired electrons decreases, the binding energy also decreases. Similarly for copper and zinc, because it is going to attain the stable electronic configuration. That is why the unpaired electrons, they are no longer available for the bond formation. So the binding energies are going to decrease. So now students, we can conclude that when we move from left to right in the d block series, the number of unpaired electrons increases up to group 5, that is vanadium family, and group 6b, which is chromium family. After that, the pairing of electrons starts. The number of unpaired electrons becomes 0 at group 2b. It means that the binding forces go on increasing up to group 5 and then decreases afterwards. Students, transition elements, they show variable oxidation states, and the reason for that is the lesser energy difference between 4s and 3d orbitals. Here is a chart which is going to show the variable oxidation states of first 3d series. Scandium is present in +2 and +3 oxidation states in most of its compounds. Similarly, titanium can attain a oxidation state up to +4, vanadium +5. The maximum oxidation state is seen by manganese, which shows oxidation states from +1 up to +7. After manganese, we have seen that unpaired electrons, they are going to decrease as the pairing is going to get started. So the oxidation state also decreases. Iron is going to have maximum oxidation states up to +6, cobalt +5, nickel +4. Copper is present in +1, +2 and +3 oxidation states, but zinc, it shows only a oxidation state of +2. Students, as we know that transition elements, they are used as catalysts as they show catalytic activities. Here are a few examples in which transition elements and their compounds are used as catalyst. A mixture of zinc oxide and chromium oxide is used for the manufacture of methyl alcohol. Nickel, platinum and palladium are catalysts for hydrogenation of vegetable oil, and saturation of alkenes and alkynes into alkanes. They are also used in Oswald's process for the manufacture of nitric acid. Manganese oxide can be used as a catalyst for the decomposition of hydrogen peroxide. Titanium tetrachloride is used as a catalyst for the manufacture of various plastics. Vanadium pentoxide is used to oxidize sulfur dioxide into sulfur trioxide, which is used in the manufacture of sulfuric acid. Iron is used as a catalyst for the synthesis of ammonia in the Haber's process, and about 1% of sodium oxide or potassium oxide and about 1% of silicon oxide or aluminium oxide are added as promoters. Now, what is a promoter? It is going to further activate the catalyst. Molybdenum is also sometimes used as a promoter. So these are few examples of transition elements as catalysts. Students, transition elements, they also show magnetic behavior. Many transition elements and their compounds are paramagnetic. Now, what are paramagnetic substances? The substances attracted into magnetic field are called paramagnetic substances, and this phenomena is called paramagnetism. Paramagnetism is due to the unpaired electrons present in the metals and their compounds. We have just discussed the electronic structure of transition elements, and you have seen the number of unpaired electrons which are present in the 3d orbitals. Therefore, many of the transition elements they show paramagnetic behavior. Some transition elements are ferromagnetic. The substances which can be magnetized are called ferromagnetic, means it is an induced magnetization. For example, iron, cobalt and nickel, they are ferromagnetic in nature. Substances in which even number of electrons are present and have paired spins are called diamagnetic. They are slightly repelled in the magnetic field. So students, we have seen the electronic configuration of zinc, in which all the electrons are paired up. Such substances can be repelled in the magnetic field and they are called diamagnetic substances. Students, the magnetic moment mu can also be calculated for transition elements. The magnetic moment is related to the number of unpaired electrons which are represented by n in the equation. So mu, which is the magnetic moment, is equal to the square root of n into n plus 2. It is measured in Bohr magneton. The unit is Bm. By measuring the magnetic moment, the nature of the transition metal compound and the oxidation state of the transition metals, they can be calculated. Transition elements can also form alloys. Now what is an alloy? Alloy is a homogeneous mixture of two or more than two metals. Transition metal forms alloys with each other, and the reason is transition elements have almost similar sizes. Hence, the atoms of one metal can easily take up the position in the crystal lattice of the other metal. Therefore, they form substitution alloys among themselves. For example, alloy steels are the materials in which the iron atoms are substituted by chromium, manganese and nickel due to the comparative sizes. Steel has more useful properties than iron. Similarly, brass, bronze and coinage alloys are the common alloys of the transition elements. Now students, let us study the composition of different alloys and their properties and uses. The first example is brass, which is an alloy made up of copper and zinc. The composition percentage of copper may vary from 60 to 80% and that of zinc from 20 to 40%. It is a strong alloy of copper which is soft and flexible. It does not corrode, and due to low melting point, it is easy to be used. It is used to make locks, keys, water taps, pipes, artificial jewelry, door handles, and parts of different machines. Similarly, another alloy is bronze, which is made up of copper and tin. The percentage may vary from 90 to 95% copper and 5 to 10% tin. It is strong and long lasting. It does not corrode. It is used to prepare medals, coins, badges and bullets. Besides these, decorative articles are also made up of this alloy. Another alloy is nichrome, which is made up of nickel, chromium and iron. The percentages are 60% nickel, 15% chromium and 25% iron. It is used in electric heaters and filaments of furnaces. Now students, in daily life, alloys are frequently used due to these properties. As alloys are prepared according to the requirements, their characteristics are different. Yet few properties are common, which are as follows. Alloys are comparatively cheaper. They are strong and flexible, but hard alloys they can also be prepared. They have long life because they do not corrode. They are durable, they have high melting points and they are better conductors, but non-conductor alloys they can also be prepared. Students, this was all about